Swayam Prabha. Digital India. Educated India.
Welcome to the online certification course on structural systems in architecture. So, today we are in the verge of the module 7, the week 7, that is on the tensile and the plate structure, and today we will discuss the lecture number 35, that is the last lecture on the module 7, Waffle slab and the folded plate structure. If you remember, in the last lecture we introduced the plate, and in that plate we have also introduced the two typical variety of the plate, that is called the flat plate structure and the flat slab structure. So, today we will initially discuss on the waffle slab and then the folded plate. So, the concept will be covered like below: the initially the introduction, classification, grid geometry and the advantages of the waffle slab, and then we will go to the some architectural application of that. And then we will move on to the folded plate structure, and we will introduce that one. There are actions, folded plate actions, the typical types of the folded plate, and also the architectural applications. The learning objective of this particular lecture will be: we will try to outline the structural concept for the waffle slab and the folded plate, and we will illustrate the type spurts and the various functions of those two type of typical structure. So, let us start with the introduction of waffle slab. The waffle slab are one typical type of slab, that is a plate, which are eventually made with the consistent with monolithic beams. Monolithic beams are regular, are very common for the slab, but in this case, the waffle slab case, it will be very closely spaced concrete joist, or the beams are monolithically casted with the slab. So, it is a totally integrated system with the casting. When we cast a particular slab, there are densified the two directional or maybe the unidirectional, the members of the ribs or that the joist are come together in the action of that the structural system. This particular waffle slab is also known as the coffer slab. So, what happened in the waffle slab is that in case of this particular structural system of the waffle slab, those densified beams or the ribs actually effectively increase the depth of the structure. So, what is actually mentioned over here? The depth of the structure will going to increase effectively. And this what will be the geometry of the ribs, and those are governed by the total dead load and overall span of the loading and all those kind of scenarios. And as it is a long span beams, then because of that the deflection is too much, and that is why the beams are heavily reinforced. Ribs are kept almost about a distance of 125 to wide and almost about 900 deep, or that can be the typical the situation when we can go for different type of span and different type of loading criteria also. So, now let us discuss about the type of waffle slab. The type of waffle slab are mostly of two types from the structural point of view, the load action point of view. The first one is called the one-way joist system, and the second one is the second two-way joist system. And joists are nothing but those ribs or the densified beams which spaced very closely to each other and create a heavy kind of a deck. So, in case of the one-way joist system, the beam spanning in only one direction, and these ribs are very slender in that case, and this will be actually supported by some supports the slab. The suitable long span application, in case of the long span application, the economical range is almost about 30 to 50 feet, and those voids which creates, as I told in the earlier slide, it will increase the effective depth, and in other way around, if you see, it will actually reduce the dead load. The electrical and the mechanical conduits can be passed through that. So, this in this particular section or figure, I have drawn the spacing. The spacing is almost about 900 mm if I say the spacing, and depth of these things will be like 225, 325, 425, like that, depending upon the amount of loading also, or the span also. The beams are tapered, or sometimes it is also the rectangular. So, that is depend upon the necessity of something, maybe the interior also. Ribs are almost about an average 125 millimeter wide, and in between, if that is the geometry of the slab, and in between, whenever there is a the load has to be discharged through a column, we give a kind of a other directional beam, which actually going to bind those one way ribs. Similarly, the two way joist system also can be thought of when the loading is much more increased, or maybe the span is increased. We can, instead of going with the one way rib, we can go for the two way rib or the two way joist system. Here, as I understand, and as you understand, this is the ribs are in both directions, and it has been also suitable for long span application. Economical range is almost 40 feet to 50 feet, easily it can accommodate, and it's also the reduces the voids, those grids you can use, reduce the voids. It will give you a very attractive kind of a ceiling appearance, because those voids, square or rectangular voids, can create by the virtue of the two way joist system, and those voids can be utilized for some lighting applications also. In case of the one way void system, one way rib system, what we have seen over here, in this ribs we can actually pass through some of the electrical or some kind of other kind of the water, or kind of another kind of the conduits also. And here it probably a bit difficult, but the electrical and mechanical conduits may be placed below that and in between the joist systems also. So, now let us go to the grid geometry of the waffle slab, how those grid actually going to look like, and what is the governing point to select those grids. In the grids geometry, if you say there are in case of that, there are various types. The square grids are this, it can be of square, which is very easily structurally can be handled very easily. It can be sometimes skewed grid when those two directional beams are not 90 degree, making an angle of 90 degree at the intersection. It makes some angles which is more than 90 degree, or sometimes less than 90 degree skewed kind of a. Sometimes we can go for rectangular grids also, where the junctions are of 90 degree, but the length of the or span of the distribution spacing of both the directions ribs are different. Sometimes we can go for diagonal grids also, when we can thought of a equal spacings of both the directions, but they are in the 45 degree orientation. But this waffle slab, when we look into it has some kind of association with some other parameters. There are three major parameters. The first one, these parameters are important while we are going to design whether it will be a square grid or rectangular grid or oblique grid, and what should be the depth and all those kind of things. So, in this case, the three parameters are geometry of the beam pattern, the grid relationship and the lateral space enclosure, and the consistency of the beam grid structure. So, I will discuss one after another, those three typical parameter. The geometry of the beam pattern that we have just discussed, that it may be oblique, it may be biaxial kind of a load transfer. For that, if we want to have a equal amount of area, almost equal amount of edges area, not area but equal amount of dimension for a particular area to be covered with the coffered slab, then we go for either rectangular or square grid, which will transfer the load in the perimeter beam in a biaxial action. But the same nature, same area of the equal dimensions, or more or less equal dimensions, can be thought of in a diagonal grid or oblique grid. Then it will be actually going to give a two-way or opposite side two-way load shear, or it is also known as the one-dimensional load shear. Sometimes we can go with a hexagonal kind of area, which can be actually come under the coffered with a triangular grid pattern. In this case, the transfer will be from in the triangular load transfer. So, this geometry of the beam pattern which depend upon the grids or the amount of area or the dimensions you have. The grid relationship to the spatial lateral space enclosure is also another criteria, where we can go for any kind of a grid or any we can choose any type of grid because of your enclosure area. So, as I have also discussed earlier, that the enclosure area, if it is square, you can go for any kind of rectangular or maybe oblique, diagonal or so, but if the enclosure area is circular or maybe a in a kind of a hexagonal shape, or if it is a narrow rectangular shape or so, then we have to decide that which type of grid is required. Next is the consistency of the grid of the structure. Consistency of the grid of the structure is something like that. If we go further 1 degree ahead of thinking how the ribs dimensions will be. So, the first can be thought of, we can thought of a homogeneous grid, where the rib dimensions or spacings are all are equal, absolutely there is no change. But this is a graded grid separator, or primary grid or the secondary grid also can be thought of. So, if you see in this particular picture, these are the lines which I am going to mark are having the primary locations of the grid, and those primary locations of the grid are further subdivided into the smaller grids with the thinner ribs. And finally, we can go for the concentric grid or centralized kind of a concentric grid also. In that case, the ribs are not in a perfectly 90 degree oriented 90 degree. They are oriented in different shape, and finally, the dimensions or the length of the grid is gradually going to reduce, and then finally go into the central location source. Let us go to the advantage of the Waffle slab. Advantage of the Waffle slab. Advantage of the Waffle slab. In the advantage of the Waffle slab, we can have lot of advantages. The first one, it is very much flexible. We can go for any kind of speedy construction. If we go for any speedy construction, we can thought of this kind of Waffle slab. The easy for the surface integration, gives good sealing appearance. It is robust and very durable. As it is made up by concrete, is fire resistance. It is also for the it is also cost effective for some long span applications. Of course, there are some typical span, as I told, the 30 feet to almost 55 feet. It is very much economical. Application point of view, there are airports, there are auditoriums, there are large hall, which is a kind of the gallery, art gallery or banquet hall, hotels. We can apply this kind of system. Now, let us go to the application of the Waffle slab in architecture. The master architect Louis I. Kahn, one of his work, if you see in the Yale University art gallery, you see the pictures are given, which are one of the interesting type of the Waffle slab. What he has designed as a particular interior exposed ceiling with a waffle slab applied as a long span architectural solutions, and there are one way grid. Of course, there are one way grid, the major grids are like this, and then it has been this narrow channels are actually subdivided into the triangles or so. So, it creates a the wonderful interiors. And next one is the another one which is in the history of architecture we have seen in the Pantheon Rome, which is a kind of the grid structure, but this is under a dome. The Chhatrapati Shivaji International Airport, Mumbai, if you have gone to that particular the airport, it's marging out a grid the grid structure or this coffered slab structure from a column, very interesting. From a circular columns, the grids or the coffered are marging out like a mushroom kind of a thing. So, this grid, after this grid structure, let us go to the folded plate structure, which is another very interesting type of the structural systems comes under the plate. Here the folded plate is an example of the three dimensional space structure, which is a composition of the various strips of the plates also, and these plates are very rigidly placed with each another together with a kind of a rigid connectivity. It gives a very firm resistance structure also. This folded plates, if you change the orientation of the plates, each plates with other, it will give you the rigidity. We will see that how we can prove that gives you a rigidity. So, if you see the folded plate action, suppose there is a paper and there are two supports, the paper will going to bend, you see this paper will going to bend because of its own weight, self weight also. But if you can just make the paper into the in a fold and then you if you can put, and it can also able to take the own weight and self weight and some additional weight also it can actually see. This is we can see, or we can do some kind of a small experiment in our home. And if you increase the load, if you just compare the last figure and this figure, if you increase the load, instead of the one there are two such bars, the whole system can fail because of the additional load or so. But even if you go with some other the transverse direction stiffener, this is called the transverse direction stiffener, edge stiffener. If you can add to such edge stiffener to the folded the papers, it will again give you a more rigidity also. So, basically if you go through these four figures, four photograph or four sketches, then you will see that this fold, the same material, almost maybe the same length, can of having same span, can take better load if it is under fold. So, that is why a folded plate is can be applied in a long span instead of a flat plate. So, what happened in this folded plate, if you see very carefully, those are the plates, those are the single plates, and they are oriented in some angles, create a triangular kind of a folded plate. So, this bend and this corner are actually the stiffener. Because of this bend you have created, that particular bend will give you a kind of a stiffening effect, and overall the load carrying capacity of the system will going to increase. Why it is going to increase? Because it will going to act as a single slab, and the effective depth of the slab is virtually going to increase, even if you not physically increase the slab depth, but it will going to increase because of there are folds in ups and downs or the crest or in the valleys, and those are the fundamental structural the concept where from the folded plate has been derived. It increases the virtual depth of the structure. There are many applications in architecture, there are many applications of the folded plate kind of a structural system in the nature also. The one of the things we will now going to discuss in the coconut leaves. See, if you see very minutely a coconut leaf, if you see this particular photograph, I have taken a section 1 and section 2. If you see the section 1, it is a dense fold because it is very near to the end, and if you take the section 2, it is a very flatter kind of a fold which is along the other the free end of that particular coconut tree or maybe the palm tree. Now, I have drawn a particular thematic diagram where those lines are actually going to represent the folds, and this is the point where this particular leaves are actually attached, this particular point, and this is the stem or whatever. And so, this is actually having kind of a cantilever action, and as it is a cantilever action, this is the free support, free span of this particular cantilever beam, and that is, you can imagine this as a support. So, I have drawn also, this is the support and this is the cantilever beam. As you know, under the wind or any kind of the external loading, if you imagine this kind of a loading is there on the cantilever beam or this particular leaf, the bending moment diagram is like that, and the bending moment diagram is in the bending moment is heavy near to the support or near to this particular junction where the leaf is actually started, and because of that, this particular near this the support point is having a very high moment, and at the end it has having a very less moment. Now, you compare this flatter fold and the dense fold of this particular leaves. The condensed fold are near the support, density of it is densely fold, more rigid and counter more moment. See, this is the high moment scenario. At this very near to the this thing, there are very heavy kind of a fold, whereas the other end with the free end, near to the free end is less moment, the flatter folds towards the end, the tending flat, less rigid, counter less amount of moment. So, this is this particular part. So, see, the nature has also created the folded plate. By virtue of the densified fold, it can actually going to the resist high amount of moment, whereas in the case of the flatter kind of a folds is not that much able to, and it can be very easily understood by the leaves. In the folds, if you see a slab, if you see a folds, these folds are actually basically either having either a slab action or maybe a plate action or maybe a truss action, which I have described over here. So, in this kind of the folds where there are this kind of the truss actions are there, what happened is that in the first, these red color forces are the external force, will going to generate the force in the membrane force, which we have discussed in the in membrane structure, which is the kind of a flow of the forces will generate in the truss as a truss action and in the inclined plate. And finally, if you see those truss actions, membrane forces are given in the blue color arrows. And finally, from the two such plate, those forces are accumulated in the the lowermost point of your the junctions, and this black color arrows are generated, the forces are generated, and finally that transmit the load to the structure. So, this is the typical way the folded plate, the load path has been shared by the different plates and finally to the columns. The types of folded plates, if I want to discuss, we have three typical types. So, one is the folded plate surfaces, another is the folded plate frames, and the special kind of folded plate. So, this is the folded plate surfaces, where it is only the roof surface or maybe only typical one surface is created by the folded plate, which is very common in case of any kind of industrial structure, maybe a kind of the bus stand or maybe sometimes in the railway stations or so. So, in this particular figure, you see a roof has been generated by a triangular kind of a folded plate. If you see the other surfaces like the other walls and all, they are completely like a straightforward walls or so. The second one is the folded plate frames, where the not only the roof, but also a frame, that is the side members, the beams or maybe the walls, not beams, sorry, the columns or maybe the wall members are also generated, and with the folded plate, and the geometry of the roof and the geometry of the wall are clubbed together as a monolithic kind of a construction. The figure suggests that this the top roof structure and the wall structure are come under the different fold having a integrated geometrical pattern. and this photograph is also suggested something like that, and the folded plates are act as a wall, and the continuous folded plates are also act as a roof. The third one is this spatial folded plate structure, where a total space or total volumetric point of view a folded plate has been designed. So, this particular figure is showing that. So, you can have a kind of a geometrical shape which is comes from the surface development of typical solid, and we can use the different folds as a kind of a roof, and also merging to a kind of a the wall or so. So, this is a small shade designed for a bike to park. There may be a small tent like shapes also can think of, by virtue of we can create a kind of a temporary shelter also. So, application of the folded plate comes in the various forms, and it comes in the industry. Industrial structure can be the roof structure of the industry can be a folded plate. The stadiums are a folded plate. We have seen lot of stadiums, the airports, the auditoriums, and the hotels. So, let us go to some of the applications. This is the Delft Polytechnic at the Netherlands. If you see this particular section view, the interesting thing is that it has, if you see, the roof is a folded plate, typical folded plate, very high thickness. This thickness is very with comparable to the almost the sitting area, because it is a very, it has to actually take very large span, because you cannot have the columns intermediately. It has only in the peripheral area we can have the columns also. But interestingly, this particular auditorium is lifted from the original ground level or so. So, it is a raised floor, and in that raised floor is actually, if you see this one, this particular raised floor is the under a action of a cantilever kind of a beam, and this cantilever beam is marging out from a the column, the 2 column or maybe the 4 column in the 4 typical point, and these 2 columns which are actually taking the cantilever box kind of a beam is also connected by each other by a box structure. So, what we have discussed in the earlier presentation is that the balancing kind of a moment or balancing kind of a structural system is also present over here, where 2 such monolithic beams are 2 such monolithic columns are actually taking a overhanging kind of a beam scenario. This is another example where there is a sports center of the Switzerland, where the folded plate is acting as a wall also, and also for the roof, and it is again you see this particular figure, the height of a particular person, and the height of this particular, see, it is almost like 6 or 7 times the height of a person, the huge amount of the height of this particular wall, which can be actually constructed or structurally supported by the folded plate. This is another example of United States Air Force Academy, where overall whole space is designed as a folded plate, and those plates are interestingly designed such a way that there are some typical triangular openings, and that openings is generated by virtue of the different folded plate actions or the geometrical placement of the folded plate with a angular in direction, and those openings are finally dealt with the glass, and that allow the natural lights also. There are some airports, as I told you, in airports also there are folded plate application. This is one of the airport from Russia, where mega columns, these are the very huge mega columns, and white cross sections are supporting the folded plate and the folded plate is acting as a roof structure also. This is Yokohama International Passenger Terminus, where a 3-dimensional folded plate has been used, and the next one is the Sardar Vallabhbhai Patel Stadium at Ahmedabad. This is also, it is very interesting, the sitting gallery are camouflaged with the inclined folded plates, and those ribs, if you see minutely, these ribs are actually act as a column or a vertical column, but it is designed as a folded plate member, very interesting. So, these are the reference of this particular lecture, and in conclusion I must say that the waffle slab and the folded plates are the two very unique type of plate system, and the load distribution and the transmission is depend upon its actually close association with the beams and the slabs, and it can be actually act as a very wonderful solution for the long span structure. So, in the next lecture we will go in the module number 8, and that will be our last module, and where we will deal with the spatial structure. Thank you very much.